All right, hello. In this screencast, I wanted to walk through the simulations to equilibrate our systems that we'll ultimately use to perform our first set of solvation free energy calculations. So specifically, we will equilibrate boxes of water, acetone, ethanol, and diethylether with a single lidocaine molecule in them. Right? And so ultimately, we'll compute the solvation free energy of lidocaine in those systems. So as I mentioned before, this isn't a molecular simulation workshop. So due to the limited time we have together, right, our focus is just to try and get you up and running, performing solvation-free energy calculations. And so I'll take you through some scripts I have to help facilitate that process. And within the screencast, might go a little quickly at times in terms of getting things set up, but remember, in class, we could take all the time you want, and I'll be there to work with you to make sure that you get everything working. Here, I just want to try and create an additional resource for you if you have trouble, or after the workshop, if you want to review the material to try and do these things on your own. Okay, so I've already logged on to OSC on demand. Okay, so I'm just going to open up Pitzer shell. Okay, and actually I'm going to open up two Pitzer shells so I can have another one in case I want to point at a couple directories of interest. Okay, so as a note, when I log on to Pitzer, okay, I'm placed initially in my home directory. So your home directory consists of 500 gigabytes of backed up storage space. And when we perform our calculations, typically we don't run them from our home space, but instead we'll run them from scratch space. Okay, and so the difference is scratch space isn't backed up, and so it's a faster read-write time. So in theory, our simulation should hopefully run a little quicker. Okay, so is it really necessary for the calculations we're performing? Probably not, but it's just a habit I've always had. And then also it'll be nice because we can all put all of our files in the scratch space, so if there's anybody needs any help, it'll be easy enough for anybody to try and go in and take a peek and help them out. Okay, so when I first log in, if I type pwd, right, I'm in my home space. Okay, yours should say PMIU 0170. Mine says 0124 because that's the project that my account was initially created for. Okay. But I'm going to open up our scratch space. Okay, so to do that, I'm going to cd/fs scratch PMIU 0170. So if I do that and type ls, okay, right now there's a directory in there, complete. So complete is a directory which I'll dump all of my completed simulations. So if yours don't run, say in time, to move on to the next part, we can always look there. And then I'll create a series of example directories as we work through exercises. And so what I'm going to do is I'm going to create a directory for me. All right. So all of you should create a directory. You could use your username. I'll use mine, which is MIU0105. Okay. So my account was created back when you couldn't choose your name at will. And then next, I'm going to copy this copy of lidocaine example into the directory I just created. Okay. And actually, I probably should have renamed it, and I could do that here, right? Instead of lidocaine example, okay, I just want to call it lidocaine. And I could have done that in one swoop when I copied it, had I been thinking that far ahead. Okay, so let me just bring it up to the top. So now I have this lidocaine directory in there. And if I open it up, I have a directory set up for acetone, diethylether, ethanol, and water. So for the purpose of this exercise, we'll look at lidocaine at infinite dilution in these four systems. But you could do as many as you wanted. This is just, for our exercise. Okay. So let's start with acetone. Okay. So there's a series of directories in here. So in terms of setting up, we're going to look at initial config, which will generate our initial configuration. And then we'll perform a basic energy minimization just to remove any bad contacts that may have been created when we create our initial configuration. Then we'll have two steps of what I call NPT equilibration. First, we'll use a Berenson thermostat and barostat, which don't sample the correct symbol. But they can be good when you're just starting to equilibrate your system because they can remove some of the oscillations in your system. Okay, and then we'll perform a correct equilibration run. Okay, and so basically what we're doing is we're going to perform solvation free energy calculations for lidocaine infinitely dilute in our solvent. And so what we're going to equilibrate is a box with a single lidocaine in solution. Okay. Now, the other way you could do it is you could equilibrate a separate box for every single lambda state you'll eventually use in your free energy calculation. Okay, the computational cost really isn't much, so you could do that. Historically, I've just always equilibrated my system with a solute in my solvent, and then when we set up our free energy calculations, I'll just tack on a brief equilibration period to my free energy calculation. And I have found, at least looking at organic solvents and ionic liquids with, I guess you'd call them small solutes, things like lidocaine, that it works without a problem. Okay, but doing the other approach is just as well. Okay, so I'm going to start out with the initial config. Okay, and so if I look inside initial config, so there's a lidocaine ff.top. So actually that doesn't need to be there. The only thing that needs to be in your directory is this gbox solute sh. Okay. So if I vim gbox solute sh, okay, we'll walk through quickly what it does. Okay. So the first thing we're going to do is we're going to load Gromacs. Okay. And then we're going to copy. And so what we're going to copy is I'm going to come back over to my other terminal. And in my home directory, I have this force fields directory. Okay, and then there's a couple different force fields that I have files for, but we're going to be looking at trap united atom. And so in this directory, molecule XYZ PDB. Okay, and so essentially I just have XYZ structures of some solutes. Okay, and so here's a bunch of components that I have XYZ structures for, and then previous versions of Gromacs, XYZ was an acceptable file format. It's not anymore. Now they want PDB, and so I just use OpenBabel to convert from XYZ to PDB. Okay, so these are structures of molecules for which I have trap force fields set up. You can easily create new structures for new molecules and put new force fields together. The thing that's just important is that the order in my XYZ structure agrees with that used in my force field. Okay, and so here I have a lidocaine PDB file. Okay, and so the first thing we're going to do is we're going to copy that structure of a lidocaine molecule. Okay, and I'm going to rename it Solute PDB. Okay, now PDB is a common file format, but the structure format that Gromacs prefers and likes is of type .gro. It's still essentially an XYZ file. So we're going to use Gromacs' function editconf to convert my Solute PDB file to Solute gro file. And then next what we're going to do is Gromacs has a pretty nice tool called Solvate. And so what Solvate will do is if I have an equilibrated solvent box and I have the structure of a solute, it'll generate an initial structure with that solute solvated in that solvent. All right, so it'll give us a pretty good starting point. And so what I'm going to do next is I'm going to copy an equilibrated solvent box of acetone. So if I go back to my other terminal, okay, I have this equilibrated boxes directory. Okay, and so I have a folder corresponding to solvents at 298K and one for supercritical CO2. If I open up the one at 298K, okay, I have a bunch of solvents, right? These are all solvents for which I have equilibrated solvent boxes. Okay, so I have their ff.top is their Gromacs essentially force field file. Okay, that describes the interaction parameters and your system size, so number of molecules in the simulation that produced the GRO. And so I have that for all of these compounds. If you need something else, it's easy enough to create it. Okay, but one important note is, this say water equilibrated box was created with this force field file, right? And so you want to use them in tandem. Okay, so in this case, I will copy my acetone box and call it solvent GRO. Then I'm going to use solvate. So first I use editconf to remove periodic boundary conditions in that equilibrated box, and then I solvate it. Okay, I solvate my solute and my solvent, and I'm going to try and set it up so I have a box cubic box of length of 45 angstroms or 4.5 nanometers. Okay, and so the goal is essentially we're looking at lidocaine or solute in the infinite dilution limit. So I just want to make sure my box is big enough that if I'm at my solute looking outwards, that I don't see myself in any of those periodic images, so that we can safely ignore any potential solute-solute interactions. Okay, if you have a big protein, say, you may need to make that bigger, and then we'll need to talk about other strategies, because I don't think you'd be computing a solvation free energy in the same sense. Okay, and then the last thing that we'll do is we'll copy that acetone force field file, which we'll update for our simulation. Okay, now we're going to need to make some updates to that force field file, and I'll walk you through how to do that. Okay, but I copy it and I call it lidocaine ff.top. That's why I made the comment that that file didn't need to be in this directory when I opened it up, but it's okay, it'll get overwritten. Okay. And also remember, all these lines that begin with hashtags, those are just comments, okay, and so you can read through that for some more details. Okay, so what I'm going to do is I'm going to run this solute setup script, okay, so period / gbox solute.sh, okay, and it runs. Now if I type ls, okay, the two main outputs that you should see after it runs is an input.grow, so this is going to be our initial structure that we'll perform our simulations with, and our lidocaine force field file. Okay, and so we're going to need to make a couple of changes to that. Okay, and so let me try and walk you through exactly what we'll do. Okay, and before I open it, I'm going to go back to my force field directory. Okay, back up again, one more. Okay, and there's this molecule ITP. Okay, so ITP files are, you can just think of them as force field files. And so we're going to have to add lidocaine to our system, right? So we're going to copy this generic setup for pure acetone. We need to add lidocaine. Okay, and so if I look at a lot of the components which can be potential solutes, you'll often see two versions. One has an underscore FE, the other has nothing. Okay, so the difference between these two files is you give your molecule a name, right, in your system. So in this original lidocaine file, I call lidocaine lido. And lidocaine, this one with the underscore FE, I call it SOUT, S out, on all capitals, right? And in fact, my convention is whenever I have an ITP and I have this underscore FE, I've renamed the molecule S out. The reason for doing this is when we ultimately do free energy calculations, within our job, our MDP file, which tells Gromacs how to perform the calculation, we need to tell it which molecule is going to be our solute and which will couple and decouple. And so it's easy enough, if this were lido, to update that to lido. But if I know my free energy, the compound I'm going to do my free energy calculation on is always S out, I can just leave it as S out. And then it also makes it easier if I want to look at, say, finite concentrations, right? If I have a system of acetone with 20 lidocaine molecules in there, all right, I can have one lidocaine molecule which I tag as being my solute, and all of my other ones could be, lido, right? And so I can just, pick one of those solute molecules that I would couple and decouple. Okay, so this is ultimately going to be our free energy guy. And then just as a note, so when I have shake in there, so those are just force fields that I've set up so that if I want to do shake with the velocity of relay, it works. There's just a special way in which I need to order the atoms in my molecule. So if I want to constrain hydrogens, the hydrogen and that connected atom need to be in the same group. Okay, but those are minor, not important details. All right, so if I go back here, I need to update lidocaine ff.top. Okay, so there's a couple of things that I'm going to need to do. Okay, so one, okay, is I'm going to need to add my lidocaine force field. I'm going to need to add lidocaine to my system. I'm going to need to update, lidocaine's a larger molecule, so I need to add, generation of 1,4 interactions, and then we'll just update our comments. Okay, so we already saw where our lidocaine force field is. The next thing I'm going to do is I'm going to open up lidocaine input.grow, and I'm going to use a double bracket to get to the bottom of my file. Okay, and so what this tells me, this 744, is I have 744 molecules. All right, so one lig, this is going to be changed to S out. Right, this is our lidocaine molecule. The molecule 2 is our first acetone, right, and it goes up to 744. So what this means is if I go to lidocaine FF, is we have 743, right? Our system will have 743 acetone molecules, and then our top molecule is going to be lidocaine. Okay, and so it's important, since my lidocaine molecule comes first, that it comes first in this list. Okay, and when we looked at the .grow file, right, it had a lig on it, but that lig will be updated to S out as soon as we parse our input files. Right, we'll get a little note from Gromacs that says, "Hey, the names don't match up," but it'll automatically override it and use the value in our ITP file, which is what we want. Okay, so I just copied this information with the ITP file for acetone. I'm going to call this lidocaine for FE calculations. Okay, and then all I need to update is, instead of acetone.itp, this was lidocaine shake FE. Okay, so where the 1,4 interactions come in is most of those solute boxes, the molecules are small, so acetones, there's no 1,4 interactions, 1,5, 1,6, 1,7. And generally how force fields are set up is, interactions greater than 4 bonds apart, so 1,5, 1,6. Those interactions are treated as being full, right? So I'd have a full LJ and electrostatic interactions between those atoms separated by 4 or more bonds. Okay, but 1,4 interactions. So when I have atoms separated by exactly 3 bonds, which would make up a dihedral, typically we scale down those 1,4 interactions. Okay, and that's what's done here. So the first thing we need to update is gen pairs. So in our lidocaine force field, we'll have a big pair section where we explicitly identify all possible 1,4 interactions in our system. Okay, and so what this says is, for all those 1,4 interactions listed in my pairs list, generate LJ and electrostatic parameters for those interactions. And how we generate them is we're going to scale our LJ interactions by 0.5 and our electrostatic interactions by 0.833. Okay, and then I'll apply the same mixing rule that was used in our force field, which in this case is Lorentz-Berthelot law. And then up top, I'm just going to update my description of my system. It's a box of 1 lidocaine and 743 acetone molecules. Okay. Save and quit. Shift:/WQ. Okay, cool. So next, okay, a backup directory. Now the next thing we're going to do is we're going to go in and to minimization, and what's going to happen is we'll run a setup script that'll get our minimization simulation running up, set up. It'll run Gromacs' pre-processing, make sure we have everything we need there. And then we submit it to the queue, where it takes care of the minimization, and then the 2 equilibrations all in series. Okay, and for acetone, ethanol, and diethylether, this could take anywhere from, say, just 15 to 30 minutes. Gromacs has gotten really fast recently. And water, might take a day, but it's still pretty flippin' fast. Okay. Well, no, it didn't take a day. When I ran it, it took about 3 hours. Okay. But I don't know. As compared to grad school, which wasn't all that long ago, this is amazing. So if I open up minimization, you should have 3 files in minimization. We're going to have a setup script. We're going to have an MDP file. Okay, so an MDP file contains our simulation parameters, which tells Gromacs how to perform the calculation. Okay, and then we're going to have our job submission script. Okay, so in our MDP files, so there's an MDP file here. These other 2 equilibration directories will only have an MDP file. So when it comes to the MDP, there's nothing in there descriptive of the system. So if I have, if I want to repeat this for other molecules, and we'll go through that exercise, you can just use the same MDP file. Okay, all that you might have to do is update the name of the file, where here I use lidocaine just for consistency throughout. Okay, that ff.top, right, that's the one that describes what exactly is in our system and what force fields to go and pull and model parameters to go and pull to model the components in our system. Okay, some of them set up. Okay, and so what setup's going to do is it's going to copy from our initial config directory our grow file, our initial configuration, and our force field file. It's going to load Gromacs, and then it's just going to make sure everything's set up, right? So all the hard work was done in initial config. Okay, so once you get that down, bam, easy. Okay, so I run setup. Okay, setup runs. Okay, so you could ignore kind of the notes and such, right? The one warning is just in the PDB file, we label all of the atoms in our molecule using standard atom names: carbon, nitrogen, oxygen, hydrogen. Okay, but then in my force field file, I give them descriptors, so if I want to say go in and look at the structure, it becomes easier to know exactly what site I'm referring to in that lidocaine molecule. So all it's telling me is that the name in the PDB, which was what was used in the grow, doesn't match up. So it's going to end up overriding the PDB file and use what's in the input file. And just like sout will overwrite that lig name. Okay, so things are set up. The last thing, okay, is you're just going to look in your job submission script. So submit script. And so this one, you just need to update it to make it yours. And so, here's my job name. Okay. You'll get an email to have it set up so it'll send you an email when your job ends. So make sure you update this to your email address. If you don't use your email address, then it's very likely that both you and I will get an email from OSC checking to make sure we're properly using the facilities. And then we can you just make a request of our resources. So Pitzer has 40 processors per node. We have relatively small systems, and so if we were to request all 40 processors, Gromacs would actually run very inefficiently because our system just can't be broken up. So it's going to use domain decomposition. It just can't break up our small system to efficiently take advantage of the resources. So we'll just use 10. So wall time. Okay, so ideally you want to get the wall time as close to what you need as possible. So I have in here 12 hours. Okay, so in actuality for these systems, you could probably do 1 hour, and for water you might do something more like 4. Okay, so I'm going to update that just because I have some experience running these already earlier. But how you want to kind of approach this is in the ideal world, you'd want to get your wall clock as close to the amount of time you actually need as possible, because your wall clock is going to affect how long you sit in the queue. Okay, so if I were to request the max, I believe it's 96 hours, you're going to be sitting in the queue longer than if I were to request, say, 1 hour. Right, 1 hour will actually run immediately because it'll get put on the debug queue. But on the flip side of it, if you have no idea how long your simulation will run, make sure you're conservative and overestimate. Even if you think you know exactly how long your job will run, be a little conservative and estimate a little more. Because what happens is as soon as that wall clock request time is hit, so in this case, as soon as my job, like if I had underestimated, as soon as it hits 1 hour, the supercomputer is automatically going to kill my job. Okay, so try and get it as close to possible. Be conservative. If you have no idea, then put a big number in there. Okay, but you would update your email address. In this case, I'll update the wall clock time, although it's not necessary. And then I have this automated, so it'll take care of everything. It'll load Gromacs, open up the directory the job was submitted from, run our minimization run. Once it's done, it's going to copy, just like we did when we set up minimization, our force field file to our first equilibration, our final configuration file to our first equilibration. Then it's going to set up it's going to do our Gromacs pre-processing, run the job, and then repeat. Okay, and so, bam. Okay, so I save and quit. And then to get this to run, it's just a q sub submit job.sh. Okay, and if I do a qstat-u and my username, okay, I can see my job here. It's been properly submitted. We're sitting in the queue. Okay, if I check again, look, it's already running. Things are looking good. Okay. All right. So, in the interest of going through things, I'm backing up 2 directories. Now let's set up diethylether. Okay. So if I open up diethylether, ls, okay, everything's still there, right? I just copied essentially that template for acetone and just did a search and replace for acetone and replaced it with diethylether. Okay, so if I open up initial config, okay, this case I don't have the ff.top, must have just accidentally left it in there, and then gbox solute. Okay, now if you had just copied this directly from acetone, right, you would notice it's exactly the same. Okay, all I've done here is acetone gets replaced with diethylether. All right, so acetone gets replaced with diethylether. If you had just copied it from acetone, you could just do a search and replace. So if I do a shift : I can then do %, search, and I want to search for acetone, and I would replace with this case diethylether, right? And then G, and it would replace all of my occurrences of acetone with diethylether. Bam, Gbox is all set up for this system, all right? And so that's all I did, and so it's relatively easy and pain-free. So period / gbox solute, bam, set up. Okay, and just to show you the other case, okay, let me delete these lidocaine files. Okay, and I'm going to go back to acetone initial config. I'm going to copy their gbox solute. So if I were to open up gbox solute, right, I got acetone here, right? It tells me acetone. So I just do a shift : %, search for acetone. I'm going to call it diethylether and replace all occurrences. Bam. Okay, and just like that, my system, or this script, is set up for the case of diethylether. Save and quit. Run it again. Bam. All right, beautiful. Okay, so I'm going to look at lidocaine input.grow. Okay, I have 519 molecules. So first one is lidocaine, so that means I have 518 diethyl ethers. Okay, so if I open up lidocaine FF, okay, I have 518 diethyl ethers, one S out molecule, right? One solute, one lidocaine molecule. Come up here. Okay, so copy and paste, right? So how I copy and paste is just highlight and then click with my middle wheel. We could also use visual mode, but this is just as easy. Okay. Trap for lidocaine or FE. Change diethyl ether. Okay. To lidocaine _ shake FE. All right. And if you really wanted to automate these things, these files are pretty much set up in exactly the same way. So you could just create a script to go through and push these changes for you. Okay, I haven't done that because I still think this is fairly straightforward and easy. And at least when you first get started, all right, I've tried to automate the process for the most part, but I think it's good to go in there and look at things to make sure it's set up. Okay, and we're only running a few jobs, but if you do have a ton, right, if you ever want to crank out, say, hundreds of solvation free energy calculations, then automating is definitely desirable because it helps minimize possibility of mistakes too. Okay, so force field files updated. Okay, so now I go to minimization. Minimization, I just need to run setup. Okay, bam, and setup, right, I just use this name of lidocaine as my solute, so there's nothing to update in these guys and going from acetone to diethylether. Okay, if I look at my submission script, okay, I've updated the name to lidocaine diethyl, so I know it's diethylether compared to acetone. You'd update your email address. Okay, wall clock here is set to 12 hours. I'm going to change this to 1 2 just so it runs faster, and everything else is identical, right? And so, I haven't been calling everything. I haven't incorporated the solvent name into any of the names of the files. They're just all lidocaine, because that allows me to literally take all the files I use for, say, the acetone case and just reuse them for the others. All that needs to get updated is that FF file, which says exactly what's in my system, and so exactly what's in your system and how those molecules interact, and then that initial configuration file. Okay, but beyond that, right, they're one and the same, right? Which really makes it easy to crank these out. Okay, so I'm going to submit my second job. Okay, so if I look at the queue, right, acetone's still running. It's been running for about 5 minutes now. Diethylether hasn't started running yet, but like in the keep going. Let me go do ethanol. Okay, so ethanol, I start with initial config. Okay, run gbox solute. Okay, again, I had already went through and updated and changed acetone to ethanol, but if you just had copied from another system, you could just do a quick search and replace and update it yourself. Okay, now I'm going to go to minimization. Okay, I'm going to run my setup script here. Okay, all right, so now I have I get an error message, a fatal error, right? So part of the reason for going through and make sure we set this up is if I have a fatal error, I want to make sure I get it here before I set my job up. Okay, so I'm just going to delete the couple of files that created, go back to initial config. The issue is in my hurry, I forgot to update my FF file. Okay, so if I vim lidocaine input.grow, 930 ethanol molecules and 1 ethanol. Okay. 930 ethanols. Okay, we have 1 lidocaine. I'll copy and paste. All right. And I'm doing this risky. I have to get to class and teach at 10:05, right? So I'm so confident that we can get these all submitted that we're going to keep going. Okay, so this is lidocaine shake FE, right? If you make a typo on any of these, then it won't work because that file doesn't exist. And so when I set these up, that's why I run the pre-processing for minimization in the command window, because if that doesn't work, right, if I get to that point and it doesn't work, then I've messed something up like we just saw. But if it gets set up and it works, then for the most part, 90+% of the time, you're all set and good to go. Okay, there are going to be some cases where your simulation may crash and burn, and chances are our initial configuration might have been rather bad, or maybe there was an issue with the initial XYZ structure that leads to some really big energies initially that we need to go and fix. So, but it would be in that initial config and minimization that we would, well, essentially be an initial config that we would fix these and get things rolling. Okay, now, so I'm gonna. In minimization, I'll get my setup running. It runs this time. Okay, I'll open up my submission script. You could change your email address, and I'm going to change my wall time for this one for an hour again, just so it runs faster. Okay. Now, if we're running something like ionic liquids, so we've done lots of solvation free energy calculations with ionic liquids. Now, those are cases where we need to go through a more elaborate equilibration process. And essentially the main issue is just their dynamics are really, really sluggish. And so what they typically do there is, and the solvate command doesn't quite work the same because I have a separate anion and cation which make up my solute or solvent, and not a single compound. And so there we'll typically use pack mold to create a box, and then typically we'll start at a really high temperature. We'll do the minimization, then we'll start at a high temperature to kind of speed up the dynamics of our system and relax it. And then we'll quench it down and then equilibrate it once we get to that temperature of interest. Okay, so just submitted ethanol, so I'm going to go to water. Okay, go in initial config, run gbox solute, bam. Okay, I'm going to vim lidocaine input.grow. We have 2,902 water molecules. So if you've been paying attention, for that same 45 angstrom cubic box, we now have a ton more water molecules than we did for the others. And so you should expect water to take longer to run. So diethylether and acetone might take about 15 minutes for that equilibration to complete. This might take about 3 hours. But to put in perspective, that's still really fast for the system compared to I graduated with my PhD in 2013. If I could do a job like this in 3 hours, it'd be amazing, right? In fact, back then, if the job was done in a couple of days, that was great. Okay, so I'm going to Vim lidocaine FF. I think I've already forgotten how many water molecules I have, but okay. Fortunately, it'll give me an error message if I get it wrong. So that'll be 2902. I'll have 1 lidocaine. Okay, so I'm going to take my water section, I'm going to paste it. So this is going to load the lidocaine. Okay, and these are just comments. So in the Gromacs input files, semicolons correspond to comments. So if you have typos or anything there, it's fine. The only purpose they serve is comments for you. So if you were to come back to this in the future, you know what exactly is going on. You could just as well delete all the comments, and it would be just the same. Gen pairs, fudge LJ, fudge QQ, and now we update this, a box of 1 lidocaine and 2902 waters. Okay. So again, all this stuff after the semicolons, just documentation or comments. So essentially I'm adding documentation so that I can keep track in the future if I were to go back and look at this, know exactly what's going on. And then these hashtags, those just correspond to or indicating a keyword, where it's going to load my trap force field database, and then the models for lidocaine and water, which tell us how those molecules specifically interact. Go to minimization. Okay, and this is the setup script I run. Okay, things are good. Go to my submission script. I updated the job name already. You could update your email address. Here, if this job takes a little longer, I believe it took about 3 hours when I ran it the other day. So I'm going to request 6 just to be a little conservative. Okay. So while QSub spit job. So on day 1, if we get to equilibrating our systems, acetone, diethylether, and ethanol will likely finish through the time. Water we won't be able to look at till the next day. Okay, but the first 3 are running and going just fine. Okay, and if, to wrap things up, if I were to go to acetone, which is the first one we ran, okay, it's already in the second equilibration. Okay, and it's already over 1 nanosecond. So this thing is just flying. Okay, so that's the end of this screencast. Okay, and as we set up more systems, I'll make more. If this was a little fast in the workshop, you have my undivided attention. We'll take our time to go through getting everything set up. The purpose of this is just to kind of be a reference for you to outside of the workshop or in the future to refer back to if you have any questions. Okay, but if I were to make it too long, then you would never sit through it to watch it. Okay, and so all of those jobs are running. Okay, once the job is complete, you'll receive an email. Okay, and so with that, we'll talk to you